All right, we're going to get started before we go too much over time. So just as a recap, because I think we have a lot of new faces here, and if you're talking in the back, please stop. You can wait in line, but you have to stop talking.
There we go.
Hey, you chit-chatting. Thank you. All right, so just as a reminder for everyone, I'm Naré. I'm an investor with Voyager. We invest in early stage foundational industries of the future, energy, compute, industrials. Those are just a few examples. But across different industries, we look for faster, better, cheaper technologies than how we do things today. So let's kick it off. We got 3 of our portfolio companies here, and we're going to talk about how they're using different kinds of materials in what they're building. We got Ian from Astro Mechanica, Brian from Alumino, and Ankit from Conifer. I'm going to let them introduce themselves because they're going to do a much better job than me and dive into their own details about themselves and their companies. So, Ian, take it away.
All right. What's up? I am Ian, founder of Astro Mechanica.
Can you stop talking there, please? Okay, thank you.
All right. So I am Ian Brook, founder of Astro Mechanica. Background for me, lifelong in aviation, started building... Oh, yeah? Is that... All right. Oh, much better. Okay. Yeah, background, started building drone systems, early 2000s, went into building experimental aircraft, mid-2000s, built my first plane at 17, started a few companies in manufacturing, ultimately with the goal of making much better airplanes for everybody to fly on, which is what we're doing now. So, all right.
Hey, my name is Brian Harden. I've been working in solar for over 20 years. I'm not that old. I just got started early, so I got really interested in solar when I was in high school. And then I went to 4 universities, Texas, Oxford. I was a Swiss Fulbright scholar at l'École Polytechnique Fédérale de Lausanne, and then I got my PhD at Stanford in 2010. This is not my first company, it's my second. I started my first business as a grad student and developed a silver metallization paste for silicon solar cells. So my expertise is in solar, and I'll talk about that later. And that business was acquired in 2019. I spent a lot of time in China for that business. I went to China 18 times in 2 years to show that my product worked on manufacturing lines in China, which I think is really, really important because they make the best stuff in the world. And then after that, I started my new company called Alumino through a Breakthrough Energy Fellowship. Shout out to Matt over there, thank you. Also have raised a SAFE for it, and then recently had a seed funding that was co-led by Voyager.
Hey folks, my name is Ankit. I came out to the US to do my master's in data center cooling, maybe like 15 years before it became a trend. Spent my early years at Google doing data center R&D. Started a company in 2016, scaled that over the next 4.5 years, sold it, and then started Conifer. At Conifer, we are about building we're actually the only rare earth-free electric motor and powertrain platform that still performs better from power density, compactness, and cost standpoint compared to even incumbents with rare earth. So that's what we're trying to scale now.
Awesome. So to kick it off, I want to talk about what materials you guys are all using and why you went about choosing those materials. So, Ian, you're developing engines and soon going to be full airplanes. What materials do you need in the engines? And presumably you need rare earths, right? But maybe you can talk through that, and then we can get to the airplane bodies.
Yeah, I think there's definitely the 2 different components. So I'm mostly an airplane person, and in that, it's the usual suspects. So for us, high-performance carbon fiber composites, depending on the temperature, since we do high-speed things, we will use different polymers. So for low speed, there'd be like a more typical epoxy, but there's more exotic ones, polyamide, resins, things like that for high speed.
And this is for the body, yeah?
That's for the body of the airframe, yeah. Then on the engine front, it's mostly titanium. For the engines, we source a component from Pratt & Whitney, and they have to deal with a lot of like the nightmare that we don't want to touch, that is single crystal nickel alloys. So that's a them problem. And then for the electric motors, it's all the usual ones you would expect there, so copper, things like that.
Gotcha. What do you have to take into consideration when you're choosing these materials? Like are you optimizing for heat? Is that the worst thing that you're looking for? Is it the power output? Like, Walk us through that.
Yeah, we have the unique one. So it's lightest, strongest thing, but since we go fast, like the stagnation temperature at Mach 2 is 100 C. And so you're already ruling out typical carbon fiber composites, which is what we'd use typically. And we're targeting, on the lower bound, like Mach 2.7, which is right at the limit of these higher temp composites. And if we want to go faster still, which basically is more efficient, then we have to go to titanium structures.
Okay, so the faster you go from carbon fiber, epoxy,
Like a carbon fiber,
reinforced, and then you're getting to titanium.
Yeah.
Okay, gotcha. And then the engine just stays the same in terms of the components that go in it, regardless of speed.
Yeah, that's always hot, so always titanium and nickel.
Okay, titanium and nickel. All right. Brian, your company has gone through a journey. It's called Alumino, and you guys are replacing silver in solar panels, but you guys actually have ended up using copper.
Yeah.
So tell us about the journey of why are you even going after replacing silver, and then how did you end up from aluminum to copper, and what were all the considerations there?
Yeah, sure, I can. Okay, so I see pretty young faces relative to myself. So I think the most important thing if you're looking at doing materials development is looking for the right problems to solve, rather than being I developed a cool material and I think it could be an application A, B, or C. That's called your PhD. Everyone's got interesting stories. Everyone's got a hammer. They're looking for a nail. So when you're really looking at materials development, you need to look for nails. And the biggest nail in solar is silver. So if you look at a solar module, they're basically perfect except for silver consumption. They're made from abundant non-toxic materials. We could produce terawatts of these panels if we could eliminate a lot of the silver. So silver is the second largest cost of a solar module. It's over 15% of the cost of a module. And last year we used about 20% of the silver supply. So we're about 500 gigawatts, 600 gigawatts of solar right now. If we want to get to 2 to 3 terawatts, it's really not possible with the silver consumption that we're using today. So I worked in silver before. I made silver paste in my previous business. And this is a bigger shot at replacing silver with copper, essentially. Copper is 100 times cheaper than silver. Silver's about $1,000 a kilo. Copper's about 10. And so the real key to this is how can you do it in a manufacturable way? And the way we think about doing that is by taking copper foil, using lasers to cut it into the shape, and then basically soldering it to the solar cell.
Why did you go from aluminum to copper? Is it just the cost, or?
Yeah, so originally, so we sold the business in 2019, and I had solar cells from that time, and they were using lines of silver that were 25 microns thick. And so when we first started to develop this, we're well, we can't use 25 micron thick copper foil, because if you do a techno-economic analysis, it's just too expensive. When I started getting new cells from my previous customers, they were 10 microns thick. And they have just redesigned the cells because silver is such a large cost. They're literally making new cell designs that are less efficient but use less silver. And I was oh, so I could use a thin copper. And at that point, the cost savings wasn't dramatic.
Gotcha. And are there other trade-offs, let's say the conductivity that you have to worry about, or any thermal efficiency, things like that?
Yeah, I think this goes more to the audience. So I think the key for materials development is understanding the devices that exist, right? So if you go and look at the physics of a solar cell and you look at series resistance, if you understand that the silver on there is not the bulk silver of the cell, it's the sintered silver from the paste that was printed and fired, you realize bulk copper is actually higher than sintered silver. So there's all these little things that if you really understand the technology you're working on, you can kind of go in and look to make these kind of substitutional changes.
Very cool. All right, Ankit, how about for you, the electric powertrains and motors, and by design, you guys aren't using rare earths for your magnets. Tell us why that's important, why you're avoiding them in the first place, and then what are you using instead?
Okay, I have an audience quiz question. Do you know those small gas engines that wake you up on Sunday mornings when somebody is trying to mow their lawn or blow leaves or run a small moped with? Just take a guess. How many of those exist in the world? Anybody? Brilliant. Very close, very close. There's actually 1 billion of those that exist in the world. And just to contextualize it, there's 1.4 billion cars in the world. So it's similar order of magnitude problem. And these are also pretty bad from a SOx and NOx emission standpoint. So it's, if you want to see electrification happen, this is a prime target. And one of the reasons why IC engines are so popular is because it uses simple, abundant materials, simple, abundant manufacturing processes so that you can make it anywhere. Okay? So if we need to solve the electrification problem, we cannot be dependent on complicated materials, complicated processes. It just needs to be simplified. That's what people want. That's how you can localize your supply chain anywhere, you can localize manufacturing anywhere and make a difference. So if you look at the BOM of an electric motor that goes, let's say in an EV, even a smaller EV, about 50% of the BOM is rare earth materials, rare earth magnets actually, and it's about $100 per kg. And roughly 15% of BOM on top of it is electrical steel. And by the way, 70% of that electrical steel is just wasted through the manufacturing process. So it's just junk. So that's why our founding thesis was we want to take out all fancy materials. It should be globally abundant materials, and also minimize the waste in the manufacturing process. So we use 95% lower electrical steel from an input standpoint. And instead of rare earth magnets, we use the first magnets that were ever built, discovered. That's the ferrite magnets. And actually, people found ferrite magnets in the wild. It's 86% rust because it used to be just available, and because of lightning strikes, the material used to get magnetized. That's how magnets were first discovered. And so we use simple ferrite magnets, going back to what Brian was saying, $10 per kg copper, a ferrite magnet is $5 per kg, so about 1/20th the cost of rare earth magnets.
Wow. Okay, now moving to the ferrite magnets, though, what are the trade-offs instead of rare earth magnets? Like, what are you playing with there?
Yeah, and ferrite magnets are not new, as I was talking about, and they are not known, or they're known to be poor on few fronts. First, their magnetic flux density is 1/3 that of a typical rare earth magnet with a sprinkle of heavy rare earth. And also, they are ceramic material. If you have ever had your kitchen fridge stickies fall down, you'll see like it breaks very easily. So ferrite magnets are very brittle. And so we had to solve for those challenges by making, in a motor, you have a static component called stator and a rotating component called rotor. So we actually innovated on the stator front and made it produce a lot more magnetic flux for the same mass, which is why we can use a weaker magnet. And at the same time, we solved the structural problem of spinning ferrite magnets at high speed. So we had to solve these problems. And ultimately, you're asking about heat and thermal. Every problem is a thermal problem. At the end of the day, that's how entropy works. And so you have to solve a cooling problem also when it comes to it.
Gotcha. Every problem's a thermal problem. Got it. Thank you. All right, so let's dive into the manufacturing techniques y'all are using. Brian, you're going about replacing the silver, and part of the way you're metallizing is actually kind of novel too. You're using a laser-based technique. Maybe we can dive into that and tell people how it works. Like, why do you need a laser to metallize copper onto the solar panels?
Yeah, I think this is a good thing to discuss. Like, if you look in academia at what people do with solar cells, they mainly screen print silver and fire it for silicon, but what's also really popular is electrodeposition of copper. And so you can make the most efficient solar cells in the world in a lab by electroplating copper. And this has been, and this has been known for like 30, 40 years. Everyone that's tried to commercialize that technology has failed, or has stuff that's literally 4 times more expensive to electroplate copper because of the throughput, the waste issues, than it is to just use silver today. So you can't do that. So what we're trying to do is figure out ways to transfer solid materials. So you have to start with like a foil, and then trying to do that in a unique way. And the way that we do that is by using lasers to quickly cut sheets into very, very thin wires, and then to be able to transfer that over. So there's a lot of technology in that. I would say, from a materials perspective, it's not that novel, right? Like, people use copper and they connect it to silicon all the time. It's got it in your pocket right now, right? The real challenge is, can you do that at 3,000 wafers an hour? Can you do that with like very, very high yield? It's much more an engineering challenge, And what we work on, it's very, very hard to go from 0 to 1. To make a perfect solar cell is really, really challenging. But once you do that, if you use the right robots, then you can go from 1 to 3,000 much more easily than you can, for example, with like an electrodeposition. So when you think about things, you have to think about the manufacturability of what you're doing, right? If you're coming from academia and you're like, I spin coat perovskites, like, no, that doesn't exist in real life. Like, if it's this big and you spin coat, that doesn't mean it translates with slot die coating. It's actually not true. No one I know can like deposit things uniformly with like less than 20 nanometers. So be really careful about that in terms of thinking about your businesses.
Gotcha. And then one of the things that you're selling is not the solar panels itself. So you're selling the equipment to be able to do the metallization. So maybe you can talk about how you go about manufacturing that and the consumables that go with it.
Yeah, so our goal is to sell equipment to Chinese manufacturers, and these are people that I've been working with for over a decade. That is a very uncommon business practice in the United States, and to be honest, I don't plan on making America great again. So like, we do R&D in the Bay Area because we have a lot of great people, but we'll be moving to Singapore to manufacture because I'm not dealing with this shit. So like, in general, like the key is you need to find very interested customers. So whatever you work on, like there's two things you got to worry about. You got to get funded, but you got to have a product that people actually care about. So, you know, the most important thing you can do is talk to a customer and ask them if you're a top 3 priority for them, all right? If you're not, they're never going to test your stuff, right? If you go and you talk to the CTO of the top solar companies in the world, they will say silver is a top 2 problem because they don't control it, right? They can make silicon wafers, they can make modules, they do not control the silver supply. And for that reason, they will test with us whenever we want. We just got back from China on Saturday. But if you're not, if you're like the 10th most expensive component in something, but you could mess up reliability, people do not care about you. And that will trickle down through fundraising. So you need to really talk to customers and understand what you're doing.
Perfect. Ankit, you already kind of mentioned it, but maybe we can talk a little bit more about it. The strategy for Conifer is also the manufacturability. So thinking of that, how do you scale up and do it rapidly?
Yeah, and first, I align with a lot of what you said, Brian. We, in fact, describe ourselves as a manufacturing company first. And it's really important to do that because a new hire, when they're coming in, let's say a design team, day one, they need to think about high volume manufacturing. For us, high volume means hundreds of thousands of parts in 2026, 2027, going up to 1 million parts in the next 3 years. So it really is important for us. And if you look at manufacturing, just from an ROI standpoint, there are 3 stages of investment. There is the CapEx, there is how long it takes to go from I'm starting to invest to my line is ready, and how long it takes for that line to get to a decent capacity utilization so that you can start getting ROI. And typically in motor industry, what used to happen is it's almost like building software in the 90s. Somebody gives you specifications, you think about that motor platform, you design custom tooling for it that's going to take a lot of time, take a lot of money, and your capacity utilization is poor because you're working on one platform. So we had to attack all of these 3 aspects. And the first thing we did was, as I was talking about earlier, we reinvented the stator. And in doing so, we reduced the manufacturing cost of the stator significantly by about a 10th. This is the, about 10x. This is the most expensive component in the motor manufacturing part. So first was that. And to do that, we had to come up with our own SPMs, special purpose machines, that make that motor happen. And then the setting up of line, we cut down that by 50%. And on the same line, we can make multiple motor platforms. So fans, pumps, motors, or EV motors, or robot motors, they can all be on the same platform, which means capacity utilization gets better. So that is really our thesis. How do we have like less money in, faster output from a manufacturing standpoint, and use that to fuel?
Incredible. All right, Ian. You have several different machining tools in your shop. Tell us, what do they do? Why do you need them? Why don't you like contract manufacture it out? Why are you bringing that in house? Yeah.
Yeah. I'm pretty...
Start with what you have.
Okay. Well, yeah, I've got a whole host of like everything you could need for, I guess, precision metal machining. So these are things like for us in the jet engines, it starts with VTL, vertical turning lathe. So we get these, 400-pound blocks of metal in, turn that into the blanks for the engine. That then goes into precision 5-axis mill. From there, we'll turn it into all the blade geometry, all the components there. Then gets balanced. Yeah.
Why are you guys doing the blade manufacturing versus having, I don't know, is it like Boeing or some other part manufacturer to do it?
Yeah, especially when you're doing R&D, any step of the manufacturing process that you don't do in-house, you just relinquished control to. And kind of this thing of priorities, there's going to be some contract manufacturer who has a zillion things to make for Boeing. We're not going to be their number one thing. And time and speed is the single most important thing for a startup, so you need to have this all in-house just so you can go faster.
Okay, gotcha. So it's control, precision, speed,
yeah.
And you just know you're not going to be the number one for.
Yeah, and it drives down cost of iteration. You can experiment a lot more. This is another thing. Like, you actually want to flip this around almost where you own all the manufacturing initially to figure it out. Then once you've got that figured out, yeah, you can go have the conversation with the machine shop that'll do a production run.
Gotcha. So fast iteration until you got it down, and then you can use a contract manufacturer.
Yep.
Gotcha. So you're doing the rotary blades. What else are you guys doing in-house?
I mean, we'll be doing the airframe. Yeah, I mean, we make just pretty much everything shy of, I guess, there's the FETs and things like that we get for the motor controllers. Motors right now, we're not doing in-house. That's probably like a $20 million project to do the electric motors that we use.
Yeah, because you guys are buying the motors right now.
Yeah, we've got a number, this is a perk of aerospace and why I get to do these things. In part, I like doing high performance things, so we don't have to really care about cost. It just needs to work. Because planes are amortized heavily over a lot of utilization. So yeah, we get to go for like, it goes Mach 3 and it actually survives. So yeah, same thing in the motors, just really high performance, and yeah, we've got a few vendors on that.
Gotcha. Okay, that makes sense. Now, when we're thinking, I don't know, 2, 3, 4 years ahead, you're about to be machining like engines and whole planes. How do you think about that whole scale up?
Yeah, honestly, it's like high volume for an airplane would be like 50 a year. So it's not actually that many. You can effectively use the process we're using now, but simply scaled up more. So more of the machines, more optimized assembly lines, things like that. But I picked this in part because we get to treat everything a little bit more bespoke.
Gotcha. That makes sense. And then while I'm with you, how are you thinking about supply chain redundancies nowadays? Like, has anything actually changed for you, or are you thinking about anything differently?
No, aerospace is so tied into defense that most of it, most aerospace is here domestic. Like I didn't, our metal comes from the U.S., aluminum's from Oregon, titanium will be from like Ohio.
So it's kind of intrinsic in your business already.
Yeah,
well, gotcha. And Brian, what about you? How are you thinking about supply chains? I mean, you're just completely tied up in it.
Yeah, we're less concerned about supply chain. So our machines are very cheap to make, and we could sell them for maybe like 3x what we make them for. So right now we're insensitive. Like I said, we don't plan on manufacturing in America. So there's retaliatory tariffs between the U.S. and China. We have tariffs against China for solar modules, and the Chinese have 50% retaliatory tariffs on anything we want to make going there. So it's really not feasible. So Singapore has free trade treaties with China, and it used to be with the U.S. I don't know what the status of Donald Trump's madness is, but that's a different story.
We'll find out. It could change.
Yeah, it'll change.
Okay, Ankit, supply chain redundancies, anything changing for you, or it's kind of built into your business as well by avoiding rare earths? Anything else?
Yeah, first, the rare earth shortage and blockage has been tailwind for us. Not that we were praying for it, but it's been a tailwind. We've gotten a lot of interest. But a key thesis for us is wherever we are, we have to localize the supply chain there. Because we are moving away from your typical free trade world to one where there's going to be more tariffs and more customs. So that's the thing we are solving for. We're starting from one country at a time and then having key hubs, hopefully around the world, where we can solve for that. Gotcha. And our customers are also high volume customers. And if somebody there saves $10, they get Employee of the Year award. So they really care about saving money and making sure the supply chain doesn't get blocked.
That makes sense. All right, last question for y'all. It's a fun one, hopefully. What are some areas of materials or manufacturing where you see white spaces? So like, what do you wish folks could be building solutions for?
I mean, obviously I like titanium, so.
You were going to say that?
Yeah, things that we know with that. It's more on the processing end. So there's a pretty interesting company actually working on this. I think there could be more, what are they? They're down in LA. Anyways, advanced forming. So you'll have good metallurgical properties to these sheet materials, but you want to form it in these complex compound curves. And so there's roboforming processes being done with that. I think there could be a few others on that. And also there's a good metric on this, the idiot index. And the idiot index on titanium is really quite high. It's a very abundant material, but the cost of refining it and processing it, the thing I like to think of is like, if you could get titanium for nearly as cheap as steel, well, it's a much better material, no corrosion. You could have wider spans, things like that. Like moving towards that. So if I could have anything, cheap titanium.
Titanium. Brian, what do you got for us?
Yeah, let's talk about looking for problems. So if you look at the battery industry, if you just look at the top 3 costs for the battery industry, the number 1 cost is the cathode active material, the number 2 cost is the anode active material, the number 3 cost is copper. And if you just look historically, like what money has gone in and working in these areas, lots of money in the top 2, nothing in looking at copper replacement. So I'm affiliated with a company called Chemia that's replacing copper foil with base metal alloys. It's an $8 billion market that's only growing. And I think this is how you should approach problems, right? You say, hey, I'm really interested in this industry. What are the top problems that exist? Go down this ladder and see if there's actually opportunities for you. And then the other thing I'd just say is, if anyone can figure out how to make really, really high voltage switches and transformers, I'm very interested. Talk to me. It's 4 years to get a high voltage transformer, ultra high voltage, not that like 1500 volt stuff, like really high volt. Find that and come talk to me. I'm interested.
All right, high volt switchers. Okay.
An interesting thing, at least for us, is if we look at any part that we procure, maybe 50 to 75% of the cost is in the processing of it itself. And for most parts, they serve 3 key purposes. There's either electrical conductivity, there is thermal conductivity, or there's structural part of it. So I would love more innovation on the epoxy and resin front, which can be molded into whatever shape you want. You can get good strength from it, and it has good thermal conductivity. I can send an RFQ if somebody is willing to innovate on that.
Epoxy resins that you can shape very well. Got it. Check. All right. Thank you all for being here and being on the panel. We're going to open up to the audience for questions, and we'll take it from there. Cool. Wait, am I going to be the runner? Okay. Yeah, meet me halfway. If you have a question, come up.
Thank you. I have a question for Brian. That's all right. So I'm a PhD. I slot die coat perovskites, not spin coating. I have 2 questions. That's okay. One, what's the 1 and 3 you would say biggest problems in solar? And 2, kind of fundamental. One of the reasons you do like electrodeposition or physical vapor deposition is because of the contact resistances. Like you need to diffuse the electrode. And could you talk a little bit more about how cutting these strips and putting it on, you're not going to have those contact resistance issues?
Yeah. So the answer to your last question. So we solder. And so I have like a solar simulator, and I don't see a contact resistance because of the soldering materials and the interfaces. So that's one thing that I do. I think there's only 2 things from a materials perspective that are worth working on in solar. One is like dramatic silver replacement or elimination, and the other one could be perovskites. I'm actually very bearish on those. Like, I'm actually having dinner with Henry Snaith on Monday. So like, some of my best friends from Europe invented perovskites. For people that don't know, they're a printable material, they're direct band gap, they can be very, very efficient, they're very, very fragile. And so my main concerns around that is reliability, but also just like, the future of solar in China is 25% efficient modules at 8 cents a watt. Like, who gives a crap if you make them 7 cents or if you make it 30%, right? Like, if you really look at the cost driver of solar, at that point, like, solar's done its job. 50-year lifetimes, glass encapsulants. Like, the amount of money you would need to put into a perovskite to get to a level that it's interesting is really, really hard. So, like, I don't think we can do it in America because of the cost constraints. But there are people in China that are spending a lot of money on that, and I think that we'll see what happens for very niche applications. Didn't mean to call out your research specifically. Happy to talk to you after. Okay.
This is partially for Ian since he brought it up, but open to anybody, honestly. You'd mentioned some aspects of vertical integration versus horizontal integration in your shop. I'm curious what the turning point for that is on when it's smart to vertically versus horizontally integrate. And also specifically outside of, I'll say, component manufacturing and multi-system manufacturing and integration. I'm all for the vertical integration, ready for it, but I could imagine it being a slippery slope, and a lot of places lean away from being more heavily vertically integrated. So, kind of open question, what's that turnover point? I'm sure it's different for every different technology, but is it business, is it technical, is it all of it?
Yeah, I mean, it's honestly just lead time. It's if you find out that you're waiting 6 months for a thing, and you've found this a few times, like just you have to do it yourself. So yeah, and this is the case with every vendor.
I think more than half of my burn is staff. And for most people in early stage startups, your biggest thing is just your staff. So whatever you can do to save 2 weeks, it's worth what that burn is, you know?
Hello, thank you all. Ankit, Brian, Ian, and Naré. So my question is for you, Brian. I would like to ask you, you said something about you're looking for high efficiency transformers or something like this. So I want to ask you to please develop the point and tell us about the challenges and what you need exactly. And also I would like to ask the three of you about your potential ideas about expansion in Africa. Thank you.
Sure. So I think the best thing to do to look at new ideas is to open up Perplexity Pro and start asking questions. So like in general, like I haven't looked for new ideas recently, but like I would go in and I'd really try to understand the problems, who's making these stuff, and then I'd like call up. So like for example, Siemens makes ultra high voltage transformers. I would call them. I'd be like, hey, I'd find someone that knows them. I'd be like, why aren't you tripling capacity right now? You know, and I try to find out like what their bottlenecks are. And if they're just like not willing to invest in expansion, I try to understand that market a little better. And then I would look for materials that could prevent you from having to do like a billion windings around, you know, like if there's other technology you can use. And I'd look at the material stack and find out if there's anything that's worth digging into. But I personally have not spent any time on that. I just know it's a big issue and would be something I would spend time off if I wasn't working on other things.
What materials do you anticipate as being completely inflexible in terms of replacement? You mentioned copper, titanium, mining. We're really curious, especially on the lower volume ends. There's been talk about like things like scandium for LTE equipment, things like that. Very curious to hear for your specific industry context, what will be the hardest to substitute on the lower ends, not quite rare earths, but in that realm. Yeah,
I think it's all about context, right? So if you're thinking about what makes solar impactful, it's at like the 2 terawatt and up scale, right? And to put it in perspective, we haven't cumulatively produced 2 terawatts of solar yet. We'll do it sometime soon. But like we produced 600 gigawatts last year, right? So when you're at a certain scale, you have to kind of look at like abundance charts. So the reason why silicon's so amazing, it's the 4th most abundant element on Earth, right? So like, why move away from that, you know? Iron is used for a very, very good reason. It's one of the most abundant elements. So you have to kind of understand what rules exist, and then you have to constrain yourself. So like, the crappiest thing about working in solar is I can't use gallium arsenide. Gallium arsenide is an amazing material, right? So much more efficient. You just can't deposit it, you don't have enough. You know, so from my perspective, you have to look at the market that you're dealing in. Now these guys, if you're looking at, you know, rare earths, like that's also a key consideration, but not everything is as rare as it is, right? So the other thing that's really important to notice is you have to be very careful about what people say are materials constraints. So I'm from Clean Tech 1.0, and there was billions of dollars put into thin film solar because the spot price of silicon jumped to $300 a kilo, okay? You can buy polysilicon today for $5 a kilo in China, right? And so all of these people created these huge issues around that, right? I look at lithium as the same thing. People are like, oh, lithium's going to be however many X's that we're thinking about. I'm not good with lithium, I'm not going to do it. But like, the prices have crashed for that, and people are like, oh no, it's going to come back up. It's not coming back up. I know this because I've seen this. There's someone that can sell this right now at that price, and that's the winner, and everyone needs to come to that price, or you need to have some kind of protectionism that exists. So you need to be a little careful in terms of evaluating things just based on transitions that are happening in different industries.
I have just a quick comment to add. From figuring out, you know, what is important for a company, I just think about 2 metrics which I found to be most useful. First is very simple as that materials price index, whether it's London Stock Exchange or some other stock exchange. But the second thing which is very interesting that customers are very willing to pay for or solve for is when the lead time increases. So if you can just identify in an industry what lead times are increasing, that'll give you a good sense of where demand is just much, much higher than whatever is going on. And I've seen multiple companies, startups, where it was just hard for them to enter, and they just found a lead time problem, especially post-COVID, and they were able to just get the first entry point with several customers. Because a lot of times, even rare earth for us, sometimes it is a panic-driven conversation, but most of the time it's a conversation starter. Oh, you solve rare earth also, but what about these other things? Oh, okay, you do these other things as well. So at least it gets your foot in the door when you have those conversations.
Hey guys, I think with hard tech, deep tech, I always think of non-dilutive funding and how it becomes often necessary to scale. And Ian, you mentioned like you guys are finding a hard enough pain point in the beginning that you just don't have to deal with it. It's currently what our startup does too. We just find the customer that has the highest pain point, we'll deal with economics later. But I am curious, like, what are you guys excited about from non-dilutive funding? Are you tackling it already? When do you see yourself needing to access it? And anything you can speak to that would be fascinating because top of our mind.
Yeah, so when you're really early, you got to have a low burn, right? And so my favorite thing is to go to the Molecular Foundry at Lawrence Berkeley Labs. You can write a user proposal. If it gets accepted, you can work in that lab for free for a year. You can say it's non-proprietary, and it doesn't really matter at that stage of your business. They have almost all of the characterization equipment in the world that you would want. It's a beautiful facility. The government spends $800 million a year on it. I love that place. I've started all my business out of Berkeley. The second thing you got to look at is non-dilutive funding. And Matt Purdy is back there, and he is part of the Breakthrough Energy Fellowship. And that one, along with Activate and a few others that I don't know because there's been a proliferation in the last decade, they're really good places to start. And I think it's a good positive signal. If you can get money from Activate or from Breakthrough Energy Fellows, preferably, then I think it sends a good market signal for you. And if you can't, you get feedback, and you can kind of work on that. So I would say low burn, Berkeley, and then try to get some of these initially while you really understand the market, And that's not super expensive.
Yeah, I mean, I think I didn't go very much that path where, like, we did the more conventional pre-seed, seed, ramp your way up, and it's definitely, it's a combination of, like, doing something that is showing maybe, initially it's like storytelling and like your technical chops, and there's a reason to bet on you. You're sort of making a promise, you can execute on that. And then eventually, like, I would say maybe Series A or something like that, starting to have the path to revenue, which you also just need as a business. Like, I also specifically went for a thing that could be a real business early on. So I would say that's a very important component to that. And it's like, how many steps do you need to get there? Is it venture fundable? And then divvy it up that way and show that you're executing against that plan.
I actually talk to people without having any products, and I just, because if it's not interesting, I'm not going to work on it. I start from the customer first, and then I think about what could work, which is why I have a company called Alumino that makes copper foil stuff now. So like, there's trade-offs, but it seems like a better way to go.
Gotcha. One last question. Anyone? No. Great. Well, I'm between y'all and the food and the drinks, so please help yourselves. Thank you so much for coming. Thanks for being here. I hope you take a deep appreciation of all the innovation in this room. So please chat with all our founders and everyone in the room and enjoy. Thanks for coming.